Okay, welcome to Lecture 2 of CET466 Logic Design. We had I think a relatively gentle introduction last week, but I want to step things up a little bit now that you've had a chance to read through Chapter 1 of the textbook. But let's just have a quick look. That's the textbook. I think so far I have 13 people enrolled. I think 12 people have now actually got onto the textbook. And the one person who hasn't has had zero contact with me. So I've reached out several times, but nothing's happened. I think I said last time that the middle section here is more a list of stuff that we have to cover rather than what we will cover in each week. So I probably should split this up. And in my CET236 class, I have a topics list, which is what this is, and I have a schedule. I think I should do the same. So I might see about doing that for next week. Separate topic list. Let's check my notes. So my to-do list from last week's lecture was to give a bonus grade to those who had finished the participation activity before the lecture. I did that. I then reopened that participation activity so everybody else could finish it. I needed to put together a Kano map tutorial because I think that might be useful. That's one of the pieces of paper that you picked up just now, which we'll talk about shortly. And I also noted to myself that I wanted to do a sequential design example, which is the second piece of paper that I gave. And we'll try and run through those as a tutorial today. And that's just the list of what's happening again. So participation activities are pre-lecture preparation. So I want you to do those before the lecture. The challenge activities are then post-lecture on the same material, a little bit harder. You should be able to get 100% on the participation activities. It's a little bit harder to get 100% on the challenge activities. These are like quizzes. The other piece I wanted to highlight is a project. And before we get to the time when you need to think about projects, what I thought I'd do is just put together a list of potential project or project ideas. Okay? And that's what the next thing on the list is. So this is the, if you want to grab one of each of those. Yep. This picture is an annotated picture of the board we're going to be using. And it's got lots of bells and whistles on it. And one of the things I don't like about this board is when it boots up, it doesn't do much. So it's hard to tell whether it's working or not. The older boards that we used to have, or we still have, but they're not supported by Quartus anymore. They used to make all of the LED 7-segment displays flash and count up, and they flash the LEDs, and if you did something with the buttons, it'd change what it did so you could tell that the buttons were connected. So my suggestion, first project suggestion, is to write a VHDL program that exercises all parts of the development board. Now the LEDs are easy. 7-segment displays are a little harder, but they're easy, relatively easy. Buzzer is easy. VGA output is hard. IR input is relatively easy. The temperature sensor is on an I2C bus, right? So that's a little bit of protocol in there. The IR input the boards all come with a little remote control dongle. You could do a lot of the protocol for the IR in there. And then the buttons are also pretty easy. One thing about buttons, does anybody, I don't know whether you would have covered it in 363. What's a problem with connecting a mechanical button to a digital input? Any ideas? Let me see if I can pick on someone. Okay, 466. And I don't think he's here. Again. Any ideas what might be a problem of connecting a mechanical switch up to a digital input?
Human error?
Sorry?
Human error?
Human error?
It could cause
Not really. So let's just quickly have a look here, right? So what we've got, the way you often see this is you've got that's the VCC, and then you've got this here, and you'll often do, actually let me try that again. So often what you'll get, and let me use it in a different colour. Right, if you've got VCC there, often you'll have something like this. Right, where you've got a push button there, and you take that point there and you feed that into, I don't know, say you feed it into an NAND gate. Right, if you want to, Fahim, if you want to grab one of these two. Fahim, if you want to grab one of each of the pieces of paper there, that would be good. It's for the tutorial. So this sort of organization of a switch it's called a pull-up resistor, right? So you this value here, the amount of current flowing in here is pretty negligible. Hi, could you take one of each of those? Yeah. One of each of those, please? Thank you. You're welcome. Did I? Okay. So the logical value here is high, right? It's up at VCC. the right. So when the switch is like that, I keep wanting to do that. When the switch is in this position, the logical value here is a logic 1, a high. When the switch is closed, right, so if we close the switch, then the logic at that point is a 0. Okay, why am I telling you all of this? Well, the trouble is, just say we started with the switch to the right, so it's open and we have a logic 1. If you actually measured what's happening there, right, if this is versus time, and this is VCC, and this is 0, and we go along and we press the switch, what actually happens, because it's a mechanical switch, is this. Right? So when you press that switch, it's not immediately closed because of the mechanics. And this is called bounce. So the reason I bring it up is I said that I said the list of things to do. I said the buttons were easy, but they're not necessarily that easy because of this bouncing problem. So one of the things you've got to do when you take inputs from mechanical switches on just about, it's usually digital devices, is you've got to put a bit of debounce logic in there, right? So that debounce logic will turn that red, well, you can't see it red, oh well, will turn that red, that initial plot into something that looks more like this, right? It'll change it, it'll square it up, and maybe it's a bit hard to see the colour I chose. Come on. Okay. So all I've been doing for those who entered while I was talking is I thought one thing it might be good to do is to give everybody an idea of the sort of end of semester project that you might be able to do. And these boards don't come with a nice program that exercises all of them, and it would be nice to put on those boards so that when they power up, I can see whether the 7-segment displays work, I can see whether the LEDs work, I can see whether the switches work, I can hear that the buzzer works. And that, I think that might be a fun thing to do. But I'll try and come up with 1 or 2 of these ideas each week between now and when we have to decide, so you can get a handle on the sort of thing I want you to do. Where are we? Let's get over there. Okay, so the things I want to get through today, I want to look at chapter 1 of the Zybook, the textbook, just quickly, and see if anybody has any questions or comments or feedback on it. Then I want to look at the Kano Maps tutorial, which is the 2-pager. And it should be alright. then I want to have a look at Lab 2, and I'll make an attempt at Lab 2 while you do, so that we can try and get that done. Before we do that, I do need to talk a little bit more about this connection, but I'll do that as part of the CarnoMat tutorial. And then I didn't get a sense last week that everybody was comfortable with how you can design sequential logic. So I thought the second tutorial sheet there might be useful to talk about how to go about doing that. And we'll need to look at flip-flop excitation tables and how we go about doing that design. Any questions about any of that so far? Okay. So let's see if I can. It's a bit hard to read. Oh well. So the Xi book started off really quite basic, right? Voltage and current. You should all know Ohm's law by the time you get here. V equals IR. Right? And there's the first participation activity. There's the second one. Right. And let's just keep going. Anybody have any questions about the Ohm's law, the early stuff? Huh? Okay. Right, so switches are important, and as I just talked about, because they're mechanical switches interacting with an electrical system, there's a little bit of reality being injected because of that bounce problem. Alright, and there's some various things. I don't think I've ever actually made a circuit with a vacuum tube in it. So I looked back when I did electrical engineering. I actually was taught a little bit about vacuum tubes, but never actually used one. Okay, so CMOS. Want to grab one of those of each? Yeah. Thank you. So the devices you would have used in 363, the 7.4 series devices, are generally not CMOS. The reason is because a lot of, it's a little better now, the reason is because CMOS tends to be more sensitive to static discharge, right? So the TTL, the 7.4 series TTL that you would have used is less sensitive to static discharge. And CMOS is a little bit more sensitive. However, it's better from a power perspective, and even from a manufacturing perspective these days. going. Right, so there's a very simple circuit. So the things we're interested in this course are digital signals. So ones and zeros usually. But remember, I think I mentioned in the first lecture, the values of Boolean variables in VHDL can take on lots of different other values, right? They can be high impedance. Here we mean, by digital, we mean usually ones and zeros. With the word digital is used a lot for different things and sometimes incorrectly, right? There's a whole area of I suppose it's electrical engineering or electronics engineering called digital signal processing. And the trouble with that name, digital signal processing, is that it's really not just the fact that we're ones and zeros, or it's the fact that we're also chopping the signal up into discrete time instances. So we should be good there. Okay, we've got a NOT gate, maybe. You should have all of that. AND gates, that's all right. You should have all of that. OR gates, you should know those. Actually, let's just go with that. Right, so it's not there we go. That's okay, so they're the two of the three ways we want to work with digital logic, right? We want this circuit version with it's a NOT gate, an AND gate, and an OR gate. We want this truth table version, and we also want to say the Boolean algebra version. Okay, so make sure you're clear about that. And I think everybody was okay with those. There we go. I think did anybody have anything they want me to go through with chapter 1? Basically, chapter 1 should be pretty common knowledge to you, either from 236 in terms of Ohm's law, or from physics, or the Boolean stuff you should have covered in 363 in digital circuits. Okay. So let's have a look at the first tutorial that I wanted to have a look at, the Carnot map one. So if you wouldn't mind having a look at so everybody have a look at question 1, and actually why don't we get the left hand side to have a look at question 1 and the right hand side to have a look at question 2, and then we'll compare answers. Okay, so try that. There's question 1. Write the truth table for the function and draw the logic circuit, and then try and do it using NAND Gates only. Hey, oh,
One of them seems that was that one we just you can see this side is clearly the second one you see.
okay. And I didn't leave enough room. Oh well. Oops. Okay, so what we're doing with these is we're turning a Boolean algebra expression into the a truth table initially. Okay, and the way I tend to do these when I'm doing them by hand is if I've got multiple terms, right, and here we've got this form of the right, this form here is what I'd call a sum of products form, or SOP. There's the sum, and these are the products. And I tend to take each individual term and figure out what they are. So as you can see, I've tried to figure out what AB is, what BC is, and what ABCD is. Okay? So can somebody from the left-hand side let me know what they got for X? Anybody? Nobody?
Zero, first one.
0, yeah?
0, 0,
Yeah?
0, 0, 1.
So 1 there?
Another 0, I must have missed it.
Another 0, I think, and then there's a 1.
1, 1, 0, 0, 0, 0, and then the rest are 1.
And then we start, and we got 1s all the way down from there, don't we? Okay. Everybody okay with that? Yeah? So let's have a look at the other side. So this version, this question, has a slightly different form, right? And this way of writing down a logic expression is called the product of sums. It's less common, probably because of the acronym, but it's another valid way of writing writing a Boolean expression. Okay, so what is X in this case? Can we get somebody from the... Yeah?
1.
The first one is 1. I think the first one is 0, right? We got 0 or 0 and 0 or 0. Okay, so I think the first one's 0. And then you got a... What's it? I'm going to keep going?
Yeah, the second one is also 1.
You also got that as a 1? Again, I think so. Here, A or B, let me just get a different colour.
So that should be 1.
A or B is 0, and then because both of them are 0, and C or D is 0 or 1, right? So I think that should be a 1. But then 0 and 1, which is what's happening when you do the product, is it also going to be a 0? Okay, so I think that one's a 0. It's only when you've got both of these being a 1 that you end up having a 1 as X. Okay? So I think a 1 here, and a 1 here, and a 1 here, and a 0, and then 3 ones, then another 0, and then 3 ones. Okay. So has anybody had a chance to look at, to draw the circuit for it? No? Yes? Okay, so have a go at drawing, again if you're on the left hand side, try drawing the circuit for question 1, and on the right hand side try drawing the circuit for question 2. Okay, so here you've got, you used 3 NAND gates and 2 filters. I want you to implement the same thing, but only using NAND gates, which is a NAND gate implementation. And the reason you can do that is you can write down any of these as a NAND gate. You might need more than one NAND gate to implement a NAND gate, right? Because, for example, a NAND gate is an AND gate with a no inverter, right? If you put 2 NAND gate inputs together and just put this, do the same thing with both inputs, then that NAND gate becomes a NAND. So to get an AND, 2-input AND gate out of a NAND gate, we have a NAND gate, and then the output of that NAND gate goes into 2 inputs of another NAND gate, which effectively negates the output. Right, so you end up with an overall NAND approach. So this is a, you've got a, these are NAND gates, are they? This is off the NOR gates. Okay. So this is a NOR B. So this, the output here is actually the bar of that. So we will put a bar across the top. And then this, I think you're correct. This is a another way to draw this. Another way to draw this is like this. Which is an AND, yeah, so that's correct. Okay, so I'm seeing some good things happening there. That's good. So the first way I would go about doing this, so just drawing the logic circuit, right? So this piece here. Is to basically just convert the Boolean expression to the circuit. And the way I usually do these is I write down all the inputs, and in this example it's a simple example. It's simple in that I don't need A bar, B bar, C bar, or D bar, right? But if I did, the next thing I would write down is something like that, right? So I can just get access to either the variable or the inverse of the variable. Okay? We don't need those, right, this one is A bar, this one's B bar, this one's C bar, this one's D bar. We don't need any of those in this particular example. And then I just say, okay, A, B, A and B. Right, there's A and B. And then B, C. Right, I can connect C and B. Right, so the output here. It's always useful to write what you think each intermediate term is, right? Just so that you know. Otherwise, you have to keep everything in your head, and I always find that a bit hard. So, and then the thing we want here is A, B, C, D, right? And to do that, we'll want to bring A down. We'll want to bring B down. We'll want to bring C down. And we want to bring D across. Okay? So there's our each of our product terms, our min terms, if you like, sort of. And then to get the answer, I just need to have an OR gate, right? And there's my X. Okay? So that's the way I would do that. Is everybody happy enough with that? Yeah? Okay. So let's have a look at this one. So this one, again, I don't have any of the inverted terms, so I'm just going to go A, B, C, D. Right? And then I need to form A or B. So there's an OR gate.
Gate or a NOR gate?
So again, I'm just going to draw the logic circuit. I'm not going to do the NOR version yet. Okay? So this is an OR gate. And so that's my A or B. And then I need another OR gate. And there's my C or D. And then to get X, in this case, I just need to AND them together. Okay, so there's our my answer for that one. Now the two follow-up questions to draw the same thing, the same circuit, but with either, in the first case, NAND gates only, or in the second case, NOR gates only. Why would you want to do that? See if I can. Where's it gone? Michael Ag? Why would you want to? Why would you want to just use NAND gates to implement a logic circuit, or just use NOR gates?
To make a Venn diagram?
What do you mean?
Inside the
Sorry.
So you would catch on. I have no idea.
No idea? You'll have to explain the joke to me. Let me try somebody else. Right, how about you? Any thoughts? No? Emily, any thoughts?
I don't want to simplify it.
Sort of. Simplify is partly why. So the reason. So if I were implementing this circuit, right, using those 74LS series devices, I'd have to use. I think there exists a quad 2-input AND gate chip, but then I'd have to use a 3-input OR gate as well, as a separate device. Right? And oftentimes it's better to just use a smaller number of chips. In this case, it's going to be, you're still going to probably have to use 2 chips. But if it's more complicated, it's probably going to be a smaller number of chips used if you only use AND gates, so you don't have to chop and change between the type of gate you're using. Okay, so is that a sensible thing to do? I mean, why would you do it? Well, let's look at NAND gates to start with, right? A NAND gate is like that, right? A, B, and our X on the output. Right, and the truth table is 0, 0, 0, 1, 1, 0, 1, 1. Right, is going to be, well, A and B, so AB is just 0, 0, 0, 1. But X, which is equal to A NAND B, is the inverse of that. Okay? Now the nice thing about that is I can do this. Right? So if both A and B are equal, this is equivalent to a NOT gate. Right? Even better, if I use that, and do that, it's a little silly, but now that is equivalent to an AND gate. Right? If I just put an inverter on the output of a NAND gate, I get an AND gate back. So there's another thing that you should know, which is a consequence. Has anybody come across De Morgan's law? You should have come across De Morgan's law. I think it was in chapter 1. But the consequence is that this is equivalent to that. So a NAND gate can be written as an OR gate with inverting inputs. So now you can see where I'm going, right? Now what I could do is I could use one NAND gate and use another NAND gate and put that into a third NAND gate, and now that is equivalent to an OR gate. Okay, so that's a way of getting towards implementing any circuit just using any logic circuit just using NAND gates. Right, I can put all of those together because there I've got an OR gate, I've got an AND gate, and I've got a NOT. And that's all I really need in order to implement any logic circuit. Now it's a bit funny because, for example, for the OR, right, now I've got I've got 3 gates instead of 1. But oftentimes you're better off thinking in terms of not necessarily having each signal in the circuit an active high signal. Everybody understand what I mean by active high versus active low? Yeah? No? So logic signals, we usually think about logic 1 as being plus 5 volts or plus 3.3 volts, right? You don't have to do that. You could say that logic 1 is 0 volts and logic 0 is plus 3.3 volts. Right? That inversion is called an active low signal. Right? It means that it's logic 1 when the signal is low. And we'll come back to that because it's a useful idea. So what does that mean, right? For this one, Actually, let's go back to this one. Let's think about how we can do that. Right, so let me just use a different pen. Let's go with blue. Right, we could, ooh, that's a little thick. Right, so this one, instead of this, we could say, start off with just a NAND gate. Right, and this is A and this is B. And then we could have another NAND gate. So the output of this one is A NAND B. Then we could have C going into that one. And this is B NAND C. And then we could have another big NAND gate having all four of them going into it. Right, so the output here is now A, B, C, D. Those three outputs that I put there are effectively active low outputs. Because the reason is I'm actually interested in AB rather than AB bar. I'm interested in BC rather than BC bar. I'm interested in ABCD rather than ABCD bar. So then I can use, where is it gone? I can use something similar to this. And right, I've got all my active low outputs connected to an active low input. And there's my answer. I didn't have to go through the rigmarole of converting AB bar to AB and then figuring out the OR, right? It's a useful idea to know that NAND can be an AND, an OR, and a NOT, but you don't have to do the direct conversion every time if you think about active low signals being an option, which is what I've done in this case. Okay? And the second question, right, has the same sort of issue, but now we've got a NOR gate, right? And a NOR gate, funnily enough, let's go back to purple, a NOR gate, which looks like this, can also be written as that. Okay, so an AND gate with inverting inputs. And then I can do the same thing again. Right, for this circuit, right, all I have to do for this circuit, it's probably even easier, I don't know, right, is, actually let's go with, right, there's a NOR, there's a NOR. Now these outputs are actually AB A or B bar and C or D bar. And then all I have to do to get X is convert that into another NOR gate. Right? So it's basically the same circuit, except now my intermediate signals are active low rather than active high. Any questions about any of that? Okay, so as I usually do, I can't talk for more than about an hour at a time, so let's have maybe a 10-minute break. And when we come back, we'll have a look at the second part of the tutorial, the Kano map stuff. See if I can pull up a timer.
nobody knows much about it sometimes.
Yeah.
Even the people who are supposed to be doing it.
Well, that's why we gotta use that to scare them to get moving.
Exactly.
That's my plan.
I got to talking too much. I'm just stopping and breathing.
Sorry about that.
Welcome. Let me know if I can do the digital video later.
Yeah, I just want to say it's the stuff like I was managing it.
That's it. Just let me know.
I got the email though.
You did.
What was it? Oh, ToDo. Was she known for old? Might not have been. It was a lot of work. Without even deleting the message.
No, she went on the
Okay, so that was just a gentle introduction, and then I thought I'd go a little bit overboard with various other 4 input, 1 output functions, and I actually. So this is a bit silly, but this document is written in a thing called LaTeX. It's a word processing system, an older one. But the thing I like about LaTeX is that it is sort of a programming language. And while it's not what you see is what you get, oftentimes I can, as a software person, I can write what I want pretty easily. And what I did with this one is every time I build this document with LaTeX, it changes this column, all of the X columns. So every time I build it, it gives me a different random function. I haven't had one yet where every entry is a 0 or every entry is a 1, which would be a bit silly. Okay, so does everybody understand Carnot maps and how they work? Yeah, you're okay with them? Any?
No, not really. No.
Not really?
No.
Okay, so let me. What I thought I'd do is I'll do x1 as an example first, and then you can have a go at it. All right. So what I'm going to do is I'm going to go down here, maybe. And see if I can zoom in on that one and show x1. Right, so the 4-variable truth table for x1 has 2 to the 4 entries, right? So it has 16 entries. This Carnot map, 4-variable Carnot map, and there are smaller ones. There's 3-variable and 2-variable. There's larger ones. There are 5-variable and 6-variable ones. I think you can even go to, so 5 would be 2 of these, 6 would be 4 of them. 7 would be 8 of them. 8 variables would be 16 of these. Right. I'm not going to go there. I'm just going to do 4-variable. But this 4-variable Carnot map also has 16 entries. Right, 4 by 4. So I can take the information out of the. Let me see if I can do this appropriately. Maybe I can't. Should have thought about this before coming here. All right. Let's see if I can snip that. Yeah. Down a bit. I don't think I've saved the snipper. Maybe. Haven't tried the new tool, so I should do the new tool. And this is in pictures and We'll do that. And then we'll go back here. And I'll see if I can insert that picture. That's not quite what I wanted, but it's close. I should probably get a mouse for this. Oh well. There we go. Maybe. That'll do. Okay, so there's my truth table. And now what I've got to do is I've got to take each entry in the truth table, right? So this one here, or this, rather this 0 here, is in 0, 0, 0, 0. So 0, 0, 0, 0. So that there's a 0 there. 0, 0. So the first 4 are always going to be on this row. And then I want 0, 1, and that's a 1. And then I want 1, 0. Now notice the ordering here. It's not straightforward, right? So that 1, 0 is there, and then the 0 is there, right? So let's just draw that up. So this went to here. This one went to here. This one went to, oops, there. And this 0 went to there. Okay, and then I can, the next row is the 0, 1 row. So I have a 1. At 0, 1 I have a 0 with CD 0, 1. With CD 1, 0 I have a 1. And with CD 1, 1 I have a 0. Okay, so that's taking those 4 and slotting them in to that row. And then the next one, the 1, 0, again I have to skip that 1, 1 line and go to the 1, 0 row. So 1, 0, 0, 0 is a 1. 1, 0, 0, 1 is a 1. 1, 0, 1, 0 is a 0. And 1, 0, 1, 1 is also a 0. Okay, so I've taken those 4 and slotted them in there. And then the last 4 go in the 1, 1 line. 1, 1, 0, 0 is a 1. 1, 1, 0, 1 is a 0. 1, 1, 1, 0 is a 1. 1, 1, 1, 1 is a 0. Okay, everybody okay with that? So now I have the same information, but in a different form. The reason I want to do it is because I want to find the simplest possible solution or Boolean expression for x1. And the nice thing about Carnot maps is it gives me a graphical way of doing that, right? And the graphical way involves grouping ones in groups of powers of 2. So grouping them in groups of 2, 4, 8 or 16. Right? If I group two ones together, that means I can remove one of the variables, A or B or C or D. If I group four of them together, I can remove two of the variables. If I can group 8 of them together, I can remove 3 of the variables. And if everything here is a 1 or a 0, then I can obviously remove all of them because they don't matter. Okay, so let's have a look. I think this particular one I can only do groups of 2. Oh, actually, I lied. I just realized. So one thing about this Carnot map is that, and I'll draw it on one of the other ones, this edge here continues to this edge here, right? So it's like a piece of paper. You can turn it, pull it round like that so that they're like that. But additionally, this top edge also continues on the bottom edge. So I can do the same thing again. So effectively what I have here is the surface of a donut, or a toroid, if you want to use math speak. So let's have a look at what that means, right? So I'm wondering if I can do this. So I can actually group those 4 together, right? Because this edge matches over here, I can group those 4 ones together. After that, it gets a bit tricky. And let's use a different colour. Let's go with the pink though. I think it's a good idea. And so now what can I match? Well, I need, in order to get the simplest possible expression, I need to cover every term, every one, but the smallest number of times so that every one is covered. So I don't necessarily want to cover every one twice or 3 times. I only need to do it once. So here, I'm going to combine those 2 together. Right. And what else? Now I'm going to have to start recovering things, right? Because these 2, this one and this one, I will need to cover another one, or a one that's already covered if I'm grouping them. But here I can group those 2 together, and here I can group those 2 together. Okay? So that means I've got 1, 2, 3, 4 terms in my expression. So for my expression for x1 is going to have 4 terms. This big pink one, the big highlighted one, right? The trick to know which variable has been removed is which variable changes. If the variable changes, in this case A is changing, right, then it doesn't matter. So you can throw that out. And then whether it's B or D bar, it's B if the value is if B stays 1, or it's B bar if B stays 0. Here B stays 1, so it's the first part of it is B, and we remove A, and then it's a 0, the other two, the other axis, it's 0, 0, 1, 0. Right, so in this case C can be either 0 or 1, so C gets removed, and D is 0, so the expression is D bar. Okay, so that's for the pink one. So I should have done these in different colours. So let me just do them in the order that I grouped them, right? So the next one that I grouped is these two down here on 1, 0. Now there's only 2 now, so this one's going to have 3 variables in the expression. So this one, it's going to be A, B bar, and then which variable disappears? It looks like it's D disappears because D changes from between 0 and 1. So that's going to be A, B bar, and then C stays 0, so it's C bar. Okay? And then the next one I did was this one up in the top right corner. And again, this one has B changing, and A is 0, so that means it's A bar. And then the column is 1, 0, so that's C D bar. So there are 3 of the 4 groups that I've got. Now I've got to do the group that is in the top row and the bottom row. Right, so the top row and the bottom row. So the top row and the bottom row, the one that changes is A. Right? So A disappears, and B is 0, so it's going to be B bar. And then this column is 0, 1, so that's C bar D. Okay, so that's my answer for the final expression. Okay, I think that's one of the minimal answers. I'm just trying to see if there's another. Okay, another minimal answer would be if instead of doing this grouping here, right, I instead grouped these two, right? That would give me a minimal covering, but it would be a different minimal covering. Right, all of the ones would still be covered. I'd still only have 4 terms in my final expression, but it would be a different number of terms, different 4 terms. 3 of them would be the same, but that 4th one, or the one that was those 2 grouped together, would be different. Right, so I think what that means is that would be A, B bar, C bar. So I think instead of having this term, we would have A, C bar, D bar. Okay, it'd be the same as everything else, it would be the same. B, D bar, A bar, C, D bar, B bar, C bar, D. But instead of having the A, B bar, C bar term, I'd have A, C bar, D bar. Deborah, what's up?
Can you just do 2 groups instead of mixing the 4 groups or 2 groups together?
Sorry, say that again?
Can you just do grouping them into 2s instead of mixing and grouping them into 4 and 2?
I could, but I wouldn't get the simplest expression. To get the simplest expression, I need to group as many as I can to start with, and then cover all the others.
So it's not wrong if you do it in 2 groups.
Well, if I only grouped these two and then separately these two, I would then have 5 terms in this expression, right? Which would be more complicated than the one I ended up with. So it wouldn't be the simplest expression. Okay? Everybody okay with that? Okay, so I don't know what the best thing to do is. I would suggest the left-hand side here do 2, 3, and 4, and the right-hand side do say 6, 7, and 8. Okay, X6, X7, and X8, and try getting those done. And there should be you should have printed out what do you call it? Carnot maps on one of the pages. X6 is a little funky. Let me just finish these and then we'll start taking answers. Okay, let's see if we can get some answers. So I don't know what the best way to do this is. Can somebody from this side give us what you got for x2? I'll try and write it up. Right, so x, let me just use a darker colour. x2 equals, somebody? Alright. Yeah.
C naught D naught.
Sorry?
C naught D naught
C naught, D naught,
plus A
plus
plus A
B naught,
B naught
B naught,
C naught plus A naught C D plus A naught B C. That's it.
that it? Okay. That is not quite what I got. Does anybody agree? You've got something else?
Yeah, I have A bar C D
A bar C D,
plus A bar C bar D bar
A bar C bar D bar,
plus A bar B D bar
A bar B D bar,
plus A B bar A bar
A B bar D bar,
plus A B bar C bar.
plus A B bar C bar. Anybody agree with that? Nobody's agreeing.
I agree that there's 5 terms, but I'm not sure.
Okay, I agree that there are 5 terms, and let me see. I think my answer, I got that one. I got that one. And I don't think. Now it's possible you used a different covering, so it's not necessarily incorrect. But let me just check that I've got. So let's have a look at it. So this is number 2, and let's go back up here, and I'll take a screenshot again if I can figure out how to do that. And new screenshot number 2. And this is X2. I think what I might do is I'll go through this one, I'll go through one here, and then I'll put the other solutions up either in Blackboard or on YouTube or both. Okay, so that's X2. Let's go back here, find a color map that we can use, insert a picture from a file. X2, open. So the first problem with all of these sorts of issues is just transferring the data. Right, so there's X2. Let's go full screen again. Right, so let's see about X2, and we'll do X2 here. So 0, 0, 0, 0 is a 1. 0, 0, 1. That's to there. Just highlight the splits, and then it's 1, 0, 1, 1. It's 1, 1, 1. Eek! I'm doing it wrong. It's 1, 1, 1, 0, and then it's all zeros. Okay, so let's have a look. So A bars. So the way I did this one, let's just go with pink again. Right, I would look at this one here. And I see. I did it wrong. Okay, so this one here, and we need to do those, and then we need to do that. Right? Is that what you came up with? Yeah?
I only did one thing differently. On the 0, 1 row for AB, I took the 1 all the way to the right and connected them to all the way to the left.
Oh, okay. So you did this one.
Yeah.
Yeah, that is perfectly okay. One or the other, not both. Right? So that's okay. so let me just, oops, that was a 1. So let's do it your way. So, like that, right? So that is a minimal covering. You don't need to cover, you need to make sure everything's covered once, but you don't need to clobber it. So then let's have a look. Let's try the first one. So this one is A bar, C bar, D bar, right? And that's this one here. And let's do this one next. This is A bar, CD, sorry, yeah, CD. And then let's do this one going from side to side. That is A bar B. And then what changes? C changes. So it's D bar. Right? And let's do this one. So that is A, B bar, and D changes, so it's C bar. Yeah, I should have asked you for your covering first so that we don't get confused, or I don't get confused. Right, so then the last one is this one, and that is A, B bar, and then what changes? C changes, and it's D bar. Okay, we've got 5 terms, and they're each paired, so we end up with a sum of products with three terms in each, 3 variables in each. Okay, let's have a look at one of the right-hand group's problems, and let's go with x6. Let me just take a screenshot again. And then come down here and we'll maybe insert it there. Okay, so there's x6, and let's just full screen, and let's use this one as x6, right? So then it's oh, I didn't know notice there's a typo there. Okay, so x6 is 0, 1, 1, 1, 0, 1, 1, 1. And then the next one is 0, 0, 0, 1, and then the last one is 0, 1, 1, 1. Okay, can I get somebody from, how about Matthew down the back? Matt, you okay? Can you?
I actually did a few. I
E6, yeah.
You didn't do X6? Somebody done X6? Yeah, Brian? Yeah?
I have A bar D.
Or could you, just to make sure we follow the whole thing, can you tell me your covering? So what groups did you have first?
So they three groupings of four. The middle one.
So 3 groupings of 4 here, yeah? So like this,
Yeah.
1,
And then straight down.
oh, and then, oops. Let me just draw that one back. And then straight down, this one here,
Yeah.
okay? Oops. Colour, I don't want that colour. Okay, straight down.
And I did the last two and yeah. Those two.
Yeah, well, how do you group those two together?
Up and down.
Sorry, up and down?
Yeah.
So one here
And then one on the
and one here.
Yeah.
Okay. So I think that's okay. The only slight issue I have with that is those two terms, those two, are going to be a product of 3 variables. And it looks, that's why I think I mentioned it looked a bit funky to me, right? Because, let me just draw it.
I could have done that group of four.
Right, and it's usually better to make it as big as possible, right? So, and it does look funky, but it means your terms are smaller, right? So, I would have gone that way, right? Everything you did except for those 2 on the side, I would have made it groups of 4 instead of groups of 2. Okay, but give me your answer. What you got from the way you said it? Okay, so
A bar D.
A bar D,
Yeah. A bar C.
A bar C,
C D.
C D,
B C bar D.
B, B E, B C bar
D.
D,
And then B C D bar.
B C D bar. Okay. Now, what these 2 would have looked like if you'd done the groups of 4, right? This one would be B, D, and this one would be B, C. Okay, so it just makes the, let me just move it up so everybody can read it. Sorry. Right. So instead of just taking those 2 and those 2, you took the group of 4, then this term would end up being BD and this term would end up being BC. It's just a little bit simpler. Everybody okay with that? Yeah? Okay, so that gives me some homework. I will put solutions to those up in Blackboard and or on YouTube. Okay. So I want to do something a little different now. before we get there though, I want to go through lab 2, then I want you to do lab 2, and then we'll come back and I'd like to try and do that sequential design, or at least start that sequential design. We may finish it next week. Okay, but let me just quickly grab lab 2. Right, so the aim is to simulate a half adder. Didn't like me doing that. Nice little musical interlude.
Maybe I was doing last night.
That's okay. I had it there already. Okay, so. Okay, so there's the half adder truth table, right? Half adder takes 2 bits and adds them together. And because it's 2 bits, the answers can be 0, 1, or 2. Right? So the output has to be able to cope with 0, 1, or 2. And so the output, they have to have 2 outputs. The S output is the sum, and then the C output is the carry. Right, that's the next digit. So let's have a look at what that looks like. Right, so let's just have a look. So I should have thought of this before, but let's do it this way. Right, so I can, this thing I've just scrawled here is a 2-variable Carnot map. And I'm just going to put the S values in there. So 0, 0 is a 0. 1, 0 is a 1. 0, 1 is a 1. And 1, 1 is a 0. this Kano map using this SOP, the sum of product approach, can't be simplified, right? So a way to write down S is as A B bar or A bar B. But what you'll find is that there's another sort of gate that effectively looks like this on a Kano map with diagonal ones. And that's the exclusive OR. Exclusive OR is written like that in Boolean algebra. Oops, I missed it. Sorry. Let's try that again. Is that right? I think it's like that. Let me just check. I'm confusing myself. Yeah, there we go. It is that one. Right, so I can write down the sum just like that. And then the carry, well, it's just one min term, it's just AB, A and B. Okay, so that's pretty much all I have to do. Now, what I'm asking you to do in the lab is to show me that this circuit implements that truth table. So you're going to have to add a few bits and pieces to this circuit, right? I talked about a little earlier about a mechanical switch and a pull-up resistor. You're going to have to use within multisim a mechanical switch and a pull-up resistor on the input side of things in order to be able to show easily that you're changing the inputs. On the output side of things, you can connect up a lamp to the output, right? And that'll tell me whether it's on or off, whether the output is on or off, whether the lamp is on or off.
Is it a lamp? A lamp, is it?
Lamp, L-A-M-P, yeah. It's like a bulb. I think it's actually called lamp within multisim, right? Lamp forms part. In fact, let's check. I should have started it up beforehand, but let's go to apps. And you can just log in to these machines, but I don't have multisim installed on my laptop, so I'm just going to go to the app server, which is another place to do it. So you can do this stuff at home if you need to. Okay. There we go, there's multi-sim. And what do we want? Probably just a TTL. And we want an exclusive OR gate. I've forgotten, there's a NAND gate. Let's see if we can search for XOR. There we go. Quad 2 input. So be careful. See where it says open collector? That's not going to work. Right? There's a particular style of device, open collector devices, that allows you to do Boolean logic with higher currents. This will work, but you want, you need to have a pull-up resistor on the output in order to make that extra current available. So I recommend not using an open collector device. Right? 7486 is much nicer. It's just a standard. Right, there's a 7486, and I also need to search for an AND gate. Ooh, that's not really very sensible. 74LS maybe. There's a NAND gate. There we go. 7408 maybe. Okay, and then you should just be able to connect them up. So I suggest you grab a computer and have a look at that. While you're doing that, I'll try and do the lab as well, so I can show you what I meant by lamps and what I meant by switches. probe. What is going to probe? For the probe. Okay.
So you want R's with resistors as well?
Sorry?
Do you want R's with resistors as well?
Do I want, sorry.
Yeah. You have resistors on there. Do you want R's like that as well?
I would prefer you use resistors, just because for some of the more complicated circuits we might do later, it does have problems. So yeah, I would recommend putting those pull-down resistors in. Okay, so let's see if that works. Looks good to me. That's okay. So some people have managed to get it to work without pull-up and pull-down resistors. Fahim had a slightly different approach to those, and he's got it so that he's got a two-position switch. One of them's going to the ground and one of them's going to +5. That's okay. But if you've just got a single position switch, I recommend using either a pull-up resistor or a pull-down resistor. I've used a pull-down resistor because if you use a pull-up resistor, effectively logic high is when the switch is open and logic low is when the switch is closed. So I recommend using a pull-down resistor like I have here if you're doing it that way. And for this lab, I don't need you to I don't need you to write it up. All I want you to do is run the circuit, take a video of the circuit running and showing that you exercise all the inputs. So A0, B0, A0, B1, A1, B0, A1, B1, and show that the outputs are correct by the truth table, just in the video. It should take you maybe 10 seconds of video, and upload that video into Blackboard, and that is all I need you to do for this one.
Just to clarify, you'll still take it without the resistors?
I'm okay with it the way you've got it there now. That's okay.
Steps record. I don't think this is going
That's a good question. I don't know. That's actually something you should. Yeah. Well, it's okay. I wonder whether the new snipper does anything like that. I think it's just
Would you be okay with a couple screenshots of each different scenario?
4 screenshots is okay if you're happy enough to do that.
Yeah.
No. Ken Trotchley used to look after all of these, but it's been involved in a central IT now, so we have to go through the usual process of requesting software on the machine. It's just been a bit painful. I've actually been pretty impressed with it. It's less painful than I thought. It's just another level of red tape. Okay, I'm going to take another 10-minute break while you finish those up. Please try and get them done today and submitted to Blackboard. That was one of the mistakes I made last fall, is not having time in online class for doing labs. I want to make sure now that we're in person again, to make sure you have time to at least do most of the lab while these first 2 or 3 are pretty easy. The later ones may take a bit more time. I'm just going to go finish my coffee. I'll be back in about 5 minutes.
do the bottom. So keep telling me, hopefully that's some of the. Is your whole thing inverse? In the caption, I just set put the values of the truth in which sections I do it, A equals 0, B equals 0, C equals 0, X equals 0. Did you submit that online? Yeah. He's not that great to do algebra. You tell him the reason why we don't do it. Should we say signed in?
Sorry?
Should we stay signed in?
I'm tempted to try something. Should I try that? So, sorry, I'm talking to myself. The issue is for the FPGA boards, we had trouble with the drivers because the drivers that Altera make available are not signed. Because they're not signed, they had to manually go through each of these machines and install them to make sure they work. And the trouble with that is they're not quite sure they got to every machine, so I wanted to try it. But I might do that.
I mean, I have access to this computer, so I could do it. I work with Ken, so.
Oh, really?
Yeah, if you need me to do it, I'm always
I think it's,
Oh, we got you. We definitely done this one. I didn't like
So my cousin actually, so I sent you a clip, and I just want to know if it works on this. Send them out.
okay. Let me just check. Did you have a question, Rob?
No.
But my cousin, who I
It's just-
listened to years, that's the bottom of the speaker.
Yeah, what's up, John?
He's like, so I'm talking to him about this. I'm like, yo, I don't need a graphics one. He's like, which one? I'm like, any. About any.
Yeah,
He's like,
good.
good.
Yeah.
60.
I use resistance, I think like
Yeah,
that.
so that's
So-
actually
So when you use the two position right, which one?
Exactly.
You only use the one position. You only use the one position. Is it a? Yeah,
Depending on how
it is part of the.
I was thinking that, but I'm like, as long as I got my code, I'm good.
Circuit condition it's not necessarily clear what zero will do to zero or one. And you use either a pull-up resistor or a pull-down resistor to make sure it's one or the other. In this case, you may choose one or the other by using the two positions.
Let me just check your submission, Michael. Looks good to me, Michael. They've actually improved Blackboard recently in the last couple of years, so that I can actually see a lot more file types. Previously, I could only see PDF or Microsoft Word, but they extended it to be Excel spreadsheets, and now apparently videos. Now apparently videos I can see within the browser rather than having to download them and then watch them. But that,
So did mine work? It went through?
all good, yeah. So yeah, that's kind of nice. Okay. I do want to at least start the other tutorial. So let me just save that. Get out of there. And maybe kill that. Leave. There we go. Okay, so let's have a go at this this tutorial, and it's a bit complicated, so I don't think we'll get it done today. So what we'll do is I'll start it up. If you can have a look at it between now and next week, and then I'll finish it up next the first thing when we come back next week on Saturday. Okay. So design a circuit that implements the following counting. Right. So 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, and 1, 0, 0. And then the idea is it goes back to 0, 0, 0 after that. So one of the first things we've got to figure out is how many states there are. How many states are there? 2?
1, 2, 3, 4, 5, 6, 7,
8. Right? All the present state and next state is saying is we move from this state to this state. We move from this state to this state. So there's a total of 8 states. Now one of the trick questions that I gave to I don't know whether it was last year or the time before that I taught this course. One of the trick questions that I gave was I said, how many states? And I only gave the second 2 columns. I didn't give the third column. And because there are only, for whatever reason, because there are only 2 bits visible, everybody was saying, and there are only 4 different possible outputs, just about everybody said there were only 4 states. Right? But there's 2 ways to look at this. One of them is what they were doing, which is just looking at the outputs, right? What the counting is, without that third column. The other way is you've got to think about the sequence, right? And so it's worthwhile drawing the sequence as a state diagram. And a state diagram is nothing more than a circle representing each state and arrows representing the transitions from one state to the next. Right? So here we have state 0, 0, 0, and that state transitions to state 0, 0, 1. Right? State 0, 0, 1 transitions 0, 0, 1 goes to 0, 1, 1. State 0, 1, 1 transitions to state 0, 1, 0. Right. State 0, 1, 0 transitions to state 1, 1, 0. State 1, 1, 0 transitions to state 1, 1, 1. State 1, 1, 1 transitions to state 1, 0, 1. State 1, 0, 1 transitions to state 1, 0, 0. and then I didn't actually explicitly state it, but the idea is that it state 1, 0, 0 transitions. Oh, actually I did state it, I suppose. It's transitions back to 0, 0, 0. Okay, so there's my state transition diagram. This is a pretty simple state transition diagram. One of the things that can add complexity to a state transition diagram is conditionals, right? So one thing I haven't got in this case is some other input, A, say, that has to be true for that transition to take place. Right? Sometimes the other thing that could happen is I could be in state 0, 0, 0, and then depending on lots of other variables, I could transition to many other states potentially, right? Here it's just one to the next to the next. So in this example, the thing that is causing the transition is the clock cycle. Right? That's the thing that's driving whether I transition. I don't have an A, right? I don't have any other input that's telling me when to transition. So the only thing that's telling me the transition is the clock. Okay. So there's our first stab. Now I had to make sure that there were no duplicates in this list. If I didn't give you those two columns, then obviously there'd be duplicates, right? There's a 0, 1, there's a 0, 1. But there are no duplicates, so I think I'm good. There's nothing, the information I had is not hiding any state, right? If one of these, like if 111 appeared twice, then you'd have to figure out what that hidden state was doing. But it is nothing. So given that I have 8 states, how many flip-flops do I need? 3. Right. How did you get to 3?
I just did 2 to the 3.
2 to the 3, exactly. So each flip-flop, remember, think about flip-flops as 1-bit memories. Right? So 1 bit of memory can encode 2 states, a 0 state and a 1 state. So when you have more than 1 flip-flop, 2 flip-flops, 3 flip-flops, the number of states you can encode is 2 to the n, where n is the number of flip-flops. Right? So here we've got 8 states. 8 is 2 to the 3. So we can use 3 flip-flops to encode those that state information. What sort of flip-flops can we use? Can we use a JK flip-flop? Yes? No? Can we use a T flip-flop? I would suspect we can't yet. JK, yeah. We could use a JK. So a T flip-flop is a toggle flip-flop. I suspect we can't use a flip-flop that has no other input except the clock, which is what a T flip-flop does. Just toggles it out. So D, a D flip-flop. think we could potentially use a D flip-flop. What else? RS, SR, set reset flip-flop. Possibly. Let's have a look at those excitation tables, though. What's the best way to do that? Probably just Google. So let's start with the JK. And we just want images. Let's try that one. There we go, that'll do. Copy image. So let's have a look at a JK flip-flop is a flip-flop that has, well, it's got the set and reset, but let's ignore them. It's got two inputs. It's got a J input and a K input. And the present state is the state at time n. And what this is showing us is the values of the J and K inputs at that time, at the present time. And this is telling us, there's also the clock. Once that clock, and depending on the type of flip-flop, once that clock transitions high, then, and you've got a 0 on J, then this transition happens. Once you've got that happening, that clock transition happening, and you've got a 1 on J, then this transition happens. This X is saying, I don't care what happens with the input K. And these X's are saying, I don't care what happens with the input J. And this is just saying how you go from 0 to 0, from 0 to 1, from 1 to 0, from 1 to 1. Okay, let's have a look at maybe a D flip-flop excitation table. Is there a good one? Oh, maybe I should use that one. That one's got all of them. Let's try that one. Right, so there's my JK flip-flop. Now they're using T as the time rather than N like we had, but that gets me how to transition from 0 to 0, 0 to 1. There's a D flip-flop, right? Again, I can know exactly how to transition from 0 to 0, from 0 to 1, from 1 to 0, and from 1 to 1. Remember, a D flip-flop is named because it's just a delay. At the clock, it takes whatever is on the D input and presents that to the Q output. Right, so it's just a delay of one clock cycle. T is just a toggle. Right? And it looks like it's got I think this is an enable, right? Because This is like an enable input. So if it's enabled, then the flip-flop just toggles, and if it's not enabled, then it doesn't happen. So we could potentially use this sort of T flip-flop. And then SR looks okay too. Why would you choose one of these over the others? So there's several things you can think of. Usually the overriding concern is the thing that makes the circuit simplest, right? Because simpler circuits means lower cost, and that's one of the prime things we're often interested in, lowering the cost. Which one of these gives you the simplest is not necessarily clear. You may have to do a design with all four of them before you can determine that. Some problems may basically look like a D flip-flop, right? So it might be that the D flip-flop is the best. I like these two excitation tables the best, probably this one the most. The reason is because of all these don't cares. Right? If there are don't cares in there, that means I can use them or not in my design, because what I'm going to do eventually is put these into a Carnot map, and having don't cares in there is going to let me use them or not in logic minimization. And that's going to give me potentially a simpler circuit. Maybe not. The downside of this flip-flop either over one of these two is these two only need to figure out one input. JK flip-flops I've got to figure out two, so I've got to have two logic functions. So I'll see. What I might try and do is do one of these. Do this example with one type of flip-flop and then show you a way to do it with one of the other types. Okay. Okay, so there's our where's it going? There we go. So the answer to the question, what sort of flip-flops can be used? Really, any of them. Huh? We just looked at the excitation tables. Draw the K-maps for the required logic. Now, this is where it starts getting complicated, right? Right, I need to not only have my present state, next state, but then I need to say, if I'm using JK flip-flops, for example, how do I get it to go from 0 to 0, from 0 to 0, from 0 to 0, from 0 to 1, from 1? Okay. And I need to do that for each column. Right? I need to do one lot of J's and K's for this column, another lot of J's and K's for this column, and a third lot for this column. So let's just see about setting that up. What I might do, I might see if we can do this now, just using a D flip-flop, because I think that might be a bit simpler. So let's go down here and see if we can insert something. Insert a table. Now how many, we're going to have 9 rows, and 1, 2, 3, 4, 5, 6, 7, 8, 9 columns. So a 9 by 9 table. That's 10. Okay, let's just insert another table. Insert below. There we go. So what I'm going to do is do it this way. I'm going to put the column headings in first, right, for our present state, next state. And this is going to be the input for D flip-flop 3, D flip-flop 2, and D flip-flop 1. And then we'll put another printout. Oh well, let's try it here. So 0, 0, 0 goes to 0, 0, 1, I think it was. Zero, 0, 1. Is it 0, 1, 1 is the next one?
Yeah.
0, 1, 1. 0, 1, 1. What's the next one? 0, 1, 0. And then 0, 1, 0. 1, 1, 0. And then 1, 1, 0 goes to 1, 1, 1.
Yeah.
And 1, 1, 1. 1, 0, 1. 1, 0, 1 goes to 1, 0, 0. And 1, 0, 0 goes back, yeah? Okay. So let's see if we can take that snip again. And we're going to use a D flip-flop just to see if we can. Okay. See if we can get that all on the screen at once. That looks okay. Right, so now what we've got to do is we've got to go through and see what all the transitions are for, let's do Q3 to start with. Right, so 0 to 0 is the first one. That means it's a 0, right? 0 to 0, 0 to 0, 0 to 1 means it's got to be a 1. And then it goes from 1 to 1, so it's got to be a 1. Then it goes from 1 to 1 again, 1 to 1 again, so it's got to be a 1, and it goes from 1 to 1 again, and then it's a 0. Okay? And then Q2, 0 to 0 is a 0. 0 to 1 is a 1. So basically we've got to repeat Q3 of n plus 1 as the column here, right? So 0 to 1 is a 1, 1 to 1 is a 1, 1 to 0 is a 0, 0 to 0 is a 0, etc. Right? So then 1, 1, 0, 0. Okay, so now we have the functions that we've got to provide as inputs to our D flip-flops. Right? And the functions depend on the values, the inputs to those functions are Q3, Q2, and Q1, and these are the outputs. So then I need to do a let's see if I can make this a bit bigger. Right, so now I can do a 3-variable Carnot map. Right, which is basically like this. Okay, and this is I want to put D3 in there. So D3 with all zeros is a 0. D3 0 1 is a 0. The next one is also a 0. Right, and then 1 0. D3 is now 1. And 1 1, so 1. So 1 and then 1 0. 1 and 1 0 is a 1. One and 1 1 is also a 1. 1 and 0 1 is a 1, and 1 and 0 0 is a 0. Okay, so there's my Carnot map. I can now loop that out and loop that out. So I can now write down what my D3 expression is. Right? It's going to be, for this loop, it's going to be Q3 Q1. Q1. And this one, it doesn't depend on Q3, so it's going to be OR Q2 Q1 bar. Now that's a bit hard to see, sorry about that. Let's see if I make it a little bigger so that improves the visibility. Okay, so did you see the process I went through to get there? And now I have a circuit or a logic expression that I can convert into a circuit. And I need to do that 2 more times for D2 and D1. And that'll get me a circuit, and that'll allow me to make a sequential circuit. So a logic circuit that goes from state to state to state to state. I actually like this one because it's pretty simple. You could also do the same thing with a JK. The only thing with a JK, even though it's going to have more functions, those functions may be simpler because here we've got an OR. Oftentimes, because of all those don't cares in the JK flip-flop excitation table, you tend to get simpler functions. Right? So even though it maybe appear more complex because it's 2 inputs, J and K, instead of just 1, D, sometimes the logic simplifies more than this. Okay. So I haven't finished this design. We can finish the design next week. I just want to quickly say there are 2 approaches you can do for this sort of stuff. Right? The approach I've taken here is that I have to have my states identified by those numbers, right? And they have to transition that way. Sometimes it's better to not think that way. Sometimes it's better to think, well, I have 8 states. Let me just count from 0 to 1 to 2 to 3 to 4 to 5 to 6 to 7 back to 0. Right? And go and just, the reason that might be worthwhile is because there exist single chips that do that. Right? Counter chip. So I can just implement the transition information using that one chip. But then I do need to know these outputs, right? I do need to know this strange sequence. So then all that I have to do to get that is to write down my state information, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, the standard counting from 0 to 7. And then these are now outputs. Right? So when I'm in state 0, I need to give that. When I'm in state 1, I need to give that. When I'm in state 2, I need to give that. And again, that'll give me a function of the state. And I just have to, again, put together a 3-variable Carnot map. But now the actual transitions, I don't have to think about because I've already got, I can just build a normal counter. The only thing that's of interest to me is ensuring I get these outputs. Okay, that's what I'm saying here, 2 approaches. What I just showed you in detail was the state transition approach. What I just talked about quickly is decoding the numerical state to get those outputs. Oftentimes, if you are doing that sort of a design, it's good to do both, because it may not be clear just from looking at the problem which one's going to give you the cheapest solution, the simplest solution. So you're better off doing both and saying, okay, this one is definitely simpler. I had, wasn't last time, it was the time before, I had this really great problem that I thought, oh, this is so complicated, it's going to, and one of the students did it by the numerical state and it just fell straight out. It was really simple, or relatively simple. Whereas doing it from a state transition approach was way more complicated. So I suggest looking at both and choosing the best. Okay. I think that's all I have for today. So my homework is I need to split out the topic list from that schedule as a separate list. I need to go through the ToDo map solutions and post them on Blackboard or YouTube, or maybe both. I need to go through the JK version of this, and then we'll finish the D flip-flop version of this next week. Okay, but I'll post the JK version, and then we can compare the two. For you, I will post the next participation activity when I get home, or maybe this evening, and the next challenge activity to be, again, it'll be going through chapter 2 of the textbook. Any questions?